Hey guys, Pratyush here. If you have clicked on this video, then I guess you must be interested in quantum computing, or should I say, the future. Today's classical computers are good, but they are not good enough. They cannot solve some high level problems or challenges because they don't have enough computational power to do so. But a quantum computer can solve the same problems in a much faster way. Quantum computing isn't just a new version of classical computer, it's completely a new way of computing. Just as a classical bit is the basic unit of information in a classical computer, a qubit is the basic unit of information in a quantum computer, which have two basic possible states, 0 or 1. In our classical computers, the state of an event is fixed at any given time, it's either 0 or 1. But one of the properties that sets a qubit apart from a classical bit is that it can be in superposition. Superposition is one of the fundamental principles of quantum mechanics. Think of a qubit as an electron in a magnetic field. The electron's spin may be either in alignment with the field, which is known as the spin up state, or opposite to the field, which is known as the spin down state. According to the quantum law, the particle enters the superposition of states in which it behaves as if it were in both states simultaneously. In quantum superposition, it can be considered to be in both spin up and spin down at the same time, and only when we observe the system, a superposition collapse and the qubit will settle on one of its basic states. Each qubit utilized could take a superposition of both 0 and 1. Thus, the number of computations that a quantum computer could undertake is 2 to the power n, where n is the number of qubits used. A quantum computer comprised of 500 qubits would have the potential to do 2 to the power 500 calculations in a single step, and this is an awesome number. 2 to the power 500 is infinitely more atoms than in the present known universe, and this is what I call true parallel processing. The basic concept is that a classical computer can only be in one single state at a given time, but a qubit is in superposition and it's able to do parallel processing, which allows it to do certain types of problems way faster than classical computers can ever do. Let us try to understand this in another way. Imagine that you have 3 minutes to find a specific word for a problem from 100 billion possible sentences. If you search for that problem like a regular computer, one sentence at a time, you would never find it before your 3 minutes are up. But if you have 100 billion parallel realities and you could look at different sentences in each of those realities, you would find that word much faster. In this example, the quantum computer splits you into 100 billion versions of yourself to make the work easy. From this, I hope you understand some basic concept of quantum computer. So the question arises, for what purpose we can use quantum computers? Problems that are fundamentally unsolvable by classical algorithms cannot be solved by quantum algorithms either. The added value of quantum algorithms is that they can solve some problems significantly faster than classical algorithms. Quantum computers are much better than classical computers at finding the prime factors of very large number, which is the foundational principle in data encryption and data security. Some quantum algorithms are Shor's algorithm and Grover's algorithm. Shor's algorithm is a quantum algorithm for integer factorizations. Simply put, when given an integer n, it will find its prime factors. It can solve this problem exponentially faster than the best known classical algorithm can. Grover's algorithm can search an unstructured database or unordered list quadratically faster than the best classical algorithm with this purpose. Till now, we have discussed a lot about quantum computing and why it is better than classical computing. So now, let us discuss why we use electron as a qubit and what is quantum dot. An electron is extremely small and the magnetic field associated with the spin is extremely weak and thus hard to measure. However, since the spin can only point up or down, it has exactly two states. Moreover, the electron spin is subject to the laws of quantum physics. This system therefore has an ideal prerequisite to serve as fundamental building block in a quantum computer. For an electron spin to be used as a qubit, there must be a reliable way not only to determine but also to switch its direction. The scientists hope to achieve this by using a concept known as the quantum dot. In very simple terms, a quantum dot is a spherical volume, typically with diameter of 1/10,000 of millimeter, and locate inside a solid. A free electron is locked inside the sphere. The surrounding solid is built up in layers made of two semiconducting materials such as silicon and germanium and cooled to a very low temperature. To use electron spin inside a quantum dot for data processing, two conditions must be met. The superposition of the two spin states up and down must hold as long as possible, and it must be possible to change the direction of the spin very quickly. So by now I think that we have learned something about quantum computing. So if quantum computers are so cool, then why it is so difficult to build a quantum computer? A qubit demands a perfect isolation, and a slightest vibration from a nearby atom can cause a qubit to throw a quantum tantrum and lose its superposition. The difficulty is how to maintain the delicate state of superposition and entanglement to run a calculation. Well, despite from all these haunting difficulties or problems, the race to build a quantum computer is one of the most grand scientific challenges of our time. Who knows who could be the one to build the next perfect quantum computer? It might be you. What do you think? So that's all for now. Thank you all for watching. See you all in the next video. Till then, peace out.